Okay, so here we want to talk about engineering applications of complex numbers. And it says that the impedance of an inductor can be written as Z equals J times omega L, where J is the imaginary number, L is the inductance measured in H of the inductor, and omega equals 2 pi times F, where F is the frequency of the alternating current measured in hertz. If Z equals 0.25 H and F equals 0.67 hertz, find Z. Or, I'm sorry, if L equals 0.25 H and F is 60 hertz, find H. So this is very simple. What might be surprising to you is this impedance is saying that J is the imaginary number. You may be used to saying that I is equal to the square root of -1, which is might be what you got out of the pre-calculus text or other places you've seen it. But in engineering, or specifically in circuits examples, we'll use J as that imaginary number. But it means the same thing. Why does it make sense to use J? Well, as we'll see in a minute, that helps it correspond to the parallel between 2D vectors and matrices of Z. So if we talk about complex numbers, we're going to have a number Z that's equal to, for instance, A plus B times J, where A is the real part, you may also see that written as the real part of Z, and B is the imaginary part. And we use that word imaginary. That doesn't mean these are not real world problems. These come up. You need the root -1. You need these imaginary parts to solve real world problems. So that's really a misnomer. But it's in the complex plane instead of being on the real number line. And so another way to think about that is if we think about it in terms of two parts, that if this is the real number line and this is the imaginary number line, then we have something like A in this direction and B in this direction. We have some point A, B. And that should look very familiar to you from 2D vectors. If you've done that part, because we had X and Y, and we might have a point A, B, where this is A and this is B. And in 2D vectors, we might have that a force F is A in the X direction and B in the J direction. We use those unit vectors I and J. J being the Y direction. Here it corresponds to the imaginary part. So that makes sense why we use J instead of I. And the same rules apply. That for this, that Z, the magnitude of Z, is the square root of A squared plus B squared. And then we can also describe it by an angle theta, where it's the tan inverse of B over A plus 180 degrees sometimes. If we're in the second or third quadrant, sometimes we have to add. Generally, where that would be true is if A is less than 0. Okay, so that's just some general stuff about complex numbers, and we will get into our example shortly.